Thank you very much for the invitation. It's an honor to be here. Right, so I'm going to talk about, well, first I'll begin by talking about three sort of classical theorems from the 90s that are all very related. They are geometry theorems. They are proven using geometry, but they have very strong applications to number theory. I'm not going to be talking about any number theory today, but maybe I'll hint at some of the applications. So the first theorem is a theorem of Caparaso, Harris, and Mazur. Okay, so let f from x to b be a proper morphism of integral varieties such that the general fiber is a smooth curve of genus G greater than or equal to 2. Then the theorem says that there exists some integer sufficiently large and a rational, dominant rational map from some high fibered power of your family to W, a variety of general type. Okay, right, so the point of the theorem is you have a family of curves. The general fiber is a curve of general type. It's a smooth curve of G greater than or equal to 2. Then the total space of your family might not be of general type, but if you take some high enough fibered power, it emits a dominant rational map to a variety of general type. Then you have all these conjectures about rational points on varieties of general type. So for instance, one version of Lang's conjecture says that rational points in a variety of general type are not Zariski dense. That allows you to then gain information, assuming this conjecture of rational points here. And this allows you, well, allowed Caparaso, Harris, and Mazur to give uniform bounds for the number of k rational points, where k is a number field. So k rational points on a curve of genus G greater than or equal to 2, just based on the genus of the curve and the degree of the number field. And so somehow, the way I hear it is that assuming Lang's conjecture, you get these results that are extremely strong, and so maybe it leads us to believe that Lang's conjecture is not necessarily true. But I'm not going to give any opinion on that. So let me just give a definition of a variety of general type. So a variety, W, is of general type. If for any desingularization okay, maybe I didn't choose the best letter. Omega of W tilde is big. Okay. And often, actually, the way that some of this theorem and the later generalizations were proved were by proving that you have the canonical is big and that you have canonical singularities. Because if you have canonical singularities, then of course the number of sections stays okay during any desingularization. Okay, so let me just, so later there was a theorem of Hassett which said that the same is true for surfaces of general type. And then finally, there was a theorem of Abramovich. Yeah. So what I'm changing here, what I mean is now the general fiber is a surface of general type, and now the general fiber is any variety of general type. Okay. So. Right. So for instance, the most general theorem of Abramovich says that if I start with a family of varieties such as the general fiber is a variety of general type, then there exists some high fibered power such that it dominates a variety of, there's a dominant rational map to a variety of general type. So all these theorems changes what the fiber is. Okay. Right, so maybe I should just give a quick sort of example. I mean, so for instance, in this case, if you have that the total space is P1 cross a curve of general type, then of course it emits a dominant map to the curve itself, which is of general type. So So if X is P1 cross C, where C is a curve of general type. Okay, so then you have H, X to C. And sort of the first example they wrote down where you actually have to take a fibered power is if you let, let X over P1 be a family of curves given by F plus T of T times G, where F and G are quartic curves. Right, so if I take this pencil of quartic curves, then the total space is rational. It's P2 blown up at the 16 base points. But if I take the second fibered power, it turns out that it's a variety of general type. So what I want to talk about today is recent work. Okay, so I should have said some of this is joint work with Amos Turquette. And what we prove is a generalization of this theorem to the case of pairs of log general type. So a pair XD is of log general type. So first we're going to say, okay, that the pair is a log canonical pair, okay, which has been defined a few times now, and that omega x twisted by d is big. Okay. And then using this definition, the theorem that we can prove, if I take a family of stable pairs, over a smooth base, suppose the general fiber is log canonical. Okay. Then after a birational modification of the base, then there exists an integer n sufficiently large such that the pullback family such that there's a morphism from the pullback family to a pair of log general type. So let me just recap what's going on. I have a family of stable pairs. So this is a family in the moduli space of stable pairs. And the general fiber is log canonical. Then after some modification of the base, some high fiber power of my pair has a morphism to a variety of general type. Okay, so let me just, here we define in general dn is going to be the sum of the pullbacks of D through the projection maps. So I have projection maps to all of the components of X. Okay. So I should just sort of highlight sort of some of the differences between this theorem and the theorem of Caporazzo, Harris, and Mazur. So first there's this, so they prove that there's a rational map, and somehow we have to take this birational modification of the base to get away from this situation. And sort of the point is that suppose I have a map to some pair where W here is P1, then of course I can make the divisor general type. I mean, I can make the pair general type by changing the divisor. And then the rational map won't actually see the divisor. So somehow if I want to have something that's nicely defined, I have to actually have a morphism in this case. And so to get around that, we take a birational modification of the base. Okay, so I have a map from, I mean, what I want to have is really what I want to have is a map, say, from the complement to the complement. Sure, sure, okay. Oh, no, I don't see why that should be necessary. So okay, so let me define what a stable family is, and then maybe it'll clear things up. So you have a family such that the fibers have semi-log canonical singularities, and I have that kxb plus db is ample. Okay, and then I have some more technical conditions that I'm not going to mention right now, like such as Kolar's condition that says that I have this omega is twisted by d is flat and it commutes with arbitrary base change. I don't know. Are you still unhappy? Okay, so then let me just think for a moment.
When you say that there's morphism between complements, does that mean the limit on the positivity of delta to delta? It pretty much restricts what the support is, and you can't take coefficients arbitrarily large, because otherwise it won't be log canonical.
I can say that you have a map from a company to take the delta primes ample but small. Small coefficients.
Yeah.
And such that k plus delta is not
This is not ruled out.
not big. But then if you increase the coefficients of delta, then you make it
Right. You can't increase them arbitrarily because then it won't be log canonical. Go past one.
So your definition is that the complement with multiple complements.
Yeah, yeah. Is that okay?
Okay.
Okay. Okay. Right. Okay, so I mentioned briefly earlier that in the proof of the original theorems, instead of proving that for any desingularization omega is big, what they typically prove is that omega is big and that the variety has canonical singularity, so that the sections descend okay. So typically, if you read a number theory paper where they use varieties of log general type, they have a slightly different definition of log general type. So let me introduce this definition. So let X be a quasi-projective variety. So let X tilde be any desingularization. Okay. Now take a projective compactification such that the complement is a divisor D of normal crossings. then xd is of log general type. If omega yd is big. Okay. And unfortunately, these definitions don't quite agree. So the issue is that in this definition here, there's no assumption on the singularities of the complement x, the complement of d inside x. And so if there are no singularities away from the divisor, then these are the same. But if I take this pair here and I take the desingularization and I don't know anything about the singularities away from the divisor d, I'm going to have exceptional divisors, and I won't know how the sections behave through this desingularization. But if I instead use this definition of log general type, then we could prove a slightly different theorem that allows us to avoid taking the birational modification. So I'm going to, for the sake of this talk, call this openly of log general type, because somehow this is an open property of x, the complement of d inside x. So now if I just add the assumption that the general fiber is openly log canonical, by which I mean has log canonical singularities and the complement has canonical singularities. So this means, let me just say, this means xd is LC and x minus d is canonical. Then there just exists some integer m such that I actually have a morphism. To a pair openly of log general type. And somehow, since at the end of the day, the goal is to prove something about, in this case, integral points on a variety of log general type. And since all the conjectures are stated in terms of using this definition of log general type, it makes sense to also discuss this theorem. But at the end of the day, the proof of this theorem really follows from the proof of that theorem. So you don't actually have to do much more work. So how do you prove this theorem? So the main idea is that if I take a suitable family F, and I'll say what that means in a bit. Then I don't actually have a morphism. It turns out that if I take the suitable family F, that some high fiber power of my family itself is going to be a pair of log general type. And so the idea is that I could prove that if I start with a suitable family, this is of log general type, and then I could show that I have a way to get from any arbitrary family that I start with that satisfies these conditions to one of this family, one of this sort. So if families are those who have maximal variation. So roughly speaking, this means that the fibers vary as much as possible. It's sort of the polar opposite to having an isotrivial family. So a sort of more rigorous definition of this is that, well, I have some family, xd over b, and I could consider the map from my base b into the moduli space of stable pairs, which I'll denote, the compactification, I'll denote m subscript h. And then I say that the pair is a maximal variation of this map here is generically finite. has max variation. So for the next while during this talk, we're going to be assuming that the family has max variation. Okay? And then at the end, we'll show how to reduce an arbitrary family to one which is a max variation. Okay. All right, so sort of if you look at the definition I had of log general type, there's sort of two things that need to be shown, a positivity result and a singularities result. So we'll start with the positivity result. And the starting point is the theorem of Kovács and Patak-Falvy. Let f from xd to b be a family of stable pairs. Such that the general fiber is KLT. And f has maximal variation. Then for R big enough and divisible, the push forward of the relative dualizing sheaf twisted by D is big. Okay. And moreover, I believe they state this is a corollary, omega, the relative dualizing sheaf, omega f twisted by D is big. But you might be asking yourself, in my theorem, I asked for the general fiber to be log canonical, and here the general fiber is only KLT. And just a remark is that this theorem is not true for a general fiber being log canonical. So one of the difficulties is now taking this result and using it to prove something about families whose general fiber is log canonical and not just KLT. And so for the sake of this discussion, I'm going to really think in my mind that something which is KLT sort of means that the divisor D has coefficients 1 minus epsilon, where epsilon is some small number, and log canonical is when the coefficients of the divisor are 1. Okay, so sort of the first step is to take this property here, that this sheaf here is big, and relate it to the fact that some high fibered power. Right, so what I want that omega xn twisted by dn is big for n, sufficiently large. And the idea is that, well, the rough idea is that I can write omega xn b dn. Right, I could just write out precisely what this means. Right, this is just the formula for the relative dualizing sheaf. And then I could expand this out, because this one here is just the tensor product of the pullbacks from all the projections. And so the rough idea is that I know that these omega FDs are big by this theorem. I don't know anything about this one here, but if I take a sufficiently high fibered power, the positivity of this will outweigh the negativity coming from the base. But of course, this only gives me this result if the general fiber is KLT. So I need a way to extend this to having the general fiber be log canonical. And so the idea is going to be to take a Q factorial DLT modification. Because, I mean, what I really would want to do is just sort of twist here by epsilon times some divisor, but I can't because I don't know that the divisor D is Q Cartier. So a result of Haken says that if I have a family with general fiber log canonical, then the Q factorial DLT modification exists. Right. And the theorem that we will actually use is a recent result of Patak, Falvey, and Shu. And okay, so let F from X to B be a family of stable pairs. Such that the general fiber is log canonical. And suppose F has maximal variation. Then for every small enough epsilon, there exists a morphism from P, so P from Z to X, such that, okay, so Z comma delta, so okay, right. The pullback of Kx plus delta, sorry, D, is Kz plus delta. Z delta epsilon is KLT, where delta epsilon means I take delta and I reduce the coefficients of the divisor by epsilon. This family P is a stable family. P has maximum variation. And delta minus delta epsilon is effective. So, I mean, roughly speaking, this theorem gives me a way to start with some pair which is log canonical, general fiber, maximum variation, and obtain from it a birational modification to one which is KLT with maximum variation. And then I know that this result is true for KLT maximum variation, and it'll allow me to lift the sections from the one with KLT general fiber to the one with log canonical general fiber. Right, so I start with XD, which has log canonical general fiber. And I obtain a morphism, P tilde from Z tilde to X, where the pullback of Kx plus D is Kz tilde plus D, delta tilde. And here, Z tilde, delta tilde is DLT and Q factorial. Okay. And then since it's Q factorial, I could reduce the coefficients by epsilon. Right, so and now since this is a KLT pair, I could take the relative log canonical model over X. This gives me what I'm going to call Z delta epsilon. Right, and then I know from this theorem of Kovács and Patak-Falvey that, so from here I could conclude that omega Z and delta epsilon n is big, right, just sort of by reproducing what I've done here. And then because I've taken the relative log canonical model, this also tells me that these sections lift the sections on Z tilde. And now since this Z tilde is Q factorial, I could raise the coefficients of delta epsilon, delta tilde epsilon to delta tilde. So, and since this theorem tells me that the difference is effective, this is still big. And then I could just, since I know that these sections arise from the pullback of sections of the one I started with, I know that omega xn So although this theorem only gives it to me for KLT general fiber, I could still extend this result to have what I need for log canonical general fiber. Okay. So now I'll talk about singularities. Right, and so it's important to talk about the singularities because there do exist examples of varieties where omega is big, but they're not of general type because their singularities are not mild enough. And so, for example, a projective cone over a quintic curve. So if I take a projective cone over a quintic curve, I get that the dualizing sheaf is big, but the singularities don't allow me to, this is birational to project the space times the curve, so it's not of general type. Okay, so the first proposition I'm going to use is the result of Patak-Falvey. And what it says is that the total space of an SLC pair, so an SLC family, over an SLC base is SLC, right? And so this sometimes goes by the name log inversion of a junction. It tells me that if I have SLC on top, right, if I have a family where the fibers are SLC, and I have an SLC base, then the total space is SLC. And so what this gives me is that the fibered powers are SLC. Right, because I could just do this sort of inductively. I start with an SLC family over, in my case, the base is smooth. Sorry, so this is where the smoothness comes in. So in this theorem, Patak-Falvey and Zhu require that B is smooth, and that's the place where I need to require that my base is smooth. Yeah. So it just means that I'm allowed to shrink the divisor a little bit to get something which is KLT. Right, that's what I'm doing. Because yeah, so this is how far away I am from being log canonical. Right, so I start with a family where the general fiber, where all fibers are SLC over a smooth base. So I know that the total space x comma d is SLC, and then I just do this inductively to get that the fibered powers are also SLC. Right, but what I actually want is that the fibered powers are log canonical. So I need to somehow show that they're normal. Right. And if normal follows from being S2, satisfying Serre's condition S2, and being R1, so Gorenstein in codimension 1. Okay, so. Okay, so I use the definition of SLC tells me that it's S2. So really what I need to do is worry about it being R1. But this is okay because my general fiber is log canonical. And the special fiber, my singularities are in codimension 1, so in the total space they're of at least codimension 2. So I do get that my fibered powers are log canonical. Okay, so I've shown, at least in the case of maximum variation, that if I take a high fibered power of my family, it's of log general type. So what it remains to do is, on one hand, I want to also prove the theorem for pairs which are openly of log general type. And then I want to show that I could reduce any family where the general fiber is log canonical to one which is maximum variation. So first, let me just discuss how to prove this same result here for pairs which are openly of log general type. So the idea is that if I start with So I start with my family x d over b, which has general fiber log canonical and complement canonical. I know that after a base change, there exists a weak semi-stable model. All right, so this is by the thesis of Kalikaru. And so sort of the point is that if I take this weak semi-stable model, the singularities here are toroidal. And so I don't actually have to go up to a desingularization because I'm in a situation where x comma d has good singularities and the complement of x and d have good singularities. So it's sufficient to just prove that my result on this guy over here. And so again, I mean, the idea is basically the same. By the result of Kovács and Patak-Falvey, I know that omega g twisted by d prime is big. And sort of the point is that, I mean, the only difference is going to be some exceptional divisors here. And since I've assumed that the general fiber has x, the complement of d inside x canonical singularities, I only have to worry about what happens over the special fiber, because that's the only place where I don't know what happens to sections when I look at the exceptional divisor. But since this is over some isolated divisor down here, I could just twist this by some small negative multiple. Okay. So this is just pull back. And then I just do the same trick. I mean, I just now write down what the canonical of the high fibered power is here. And then once I take n powers, this thing will go away, and it cancels out exactly what I don't know about up here. And so what this tells me is that in the case of max variation, the same thing is true for a family where the general fiber is openly log canonical. Right? It tells me that if I start with maximum variation, then some high fibered power is of log general type. Okay. And so finally, we're going to need a result of Abramovich, which says that. So roughly speaking, what it says is that if I have a pair x comma d of log general type, and G a finite group, there exists some integer n sufficiently large such that the quotient is also a variety of log general type. And so the idea is very similar to what you do in the case where you don't have pairs. You just show that there are enough invariant sections vanishing to sufficiently high order that when I take the quotient by the group, things remain okay. Yeah. So in my family F, X, D to B, G should act equivariantly on this family. Okay. All right. So let me just state to be clear. So what I've shown so far is that if F from X to D to B is a family, stable family. LC general fiber over B smooth. If F has max variation, and G acts equivariantly on F, then for n sufficiently large, xn dn quotient by G is of log general type. Okay. So now what I have to do is show that if I start with any family of stable pairs with log canonical general fiber, that I could reduce to one which is of maximum variation. And we're going to do this using the moduli space of stable pairs. So the starting point is a proposition of, in the same paper, of Kovács and Patak-Falvy. And what this proposition says is that over a finite cover of the moduli space, there exists a tautological family. Okay. All right, and so the proposition that we're going to prove now says that if F is a stable family, so I'm not going to assume it has maximum variation. All I'm going to assume is that the general fiber is log canonical. Then there exists a morphism from XD to, what do I call it? The quotient of a family of maximum variation by a finite group. Right, and then the idea is that once I take fibered powers, I know that the theorem is true for families of max variation, even if I quotient by some finite group G. And then I'll have that this thing has a morphism to a variety of log general type. Okay. So I start with my family, XD over B. Okay, and I could consider the image of the base in moduli space. I'll call this sigma. And over sigma lies a universal family, so it's not a tautological family. Okay. And I know that if I take some finite cover of the moduli space, so in this case taking a finite cover of sigma, I do actually get a tautological family. But I also require in my theorem that the base is smooth. So instead of just taking a finite cover, I have to take a resolution of singularities as well. Okay, so take a finite cover of sigma. So this is going to be with Galois group G. H. And then take a equivariant resolution of singularities. So what I get at the end of the day is sigma tilde to sigma. It's a Galois cover followed by an equivariant resolution of singularities. So it's smooth and it has an action by this group H. Okay. So over sigma tilde, I have a tautological family. Okay. And I could consider the quotient by H. And I'm just going to take the fiber product here. Okay. And then I have maps like this. Okay. So what are the general fibers here? So the general fiber here is just a variety of log general type quotient by its automorphism group, right? Because this is just universal family. It's not a tautological family. It also keeps track of the automorphism. Sorry, so the general fiber here and I'm going to call this automorphism group K. Okay? And I know it's finite because the automorphism group of a pair of log general type is finite. And the general fiber here gets rid of the automorphisms, right? So it's just a pair of log general type. So now there's one thing sort of missing in this diagram. I have the quotient by H, but I could also take the quotient by K. So let me take that now. Okay, so here I just took the pullback. But what fits into this diagram is if I take T epsilon d, sorry, sigma, and I quotient by H times K. Okay. And what we're going to claim is that this map here is normalization. So why am I doing this? The point is that I have a map from xd to this guy. After I take a base change, I have a map to this guy. But I actually want a map to one whose maximum variation quotient by a finite group, which is precisely what I have here. So what I need to show is that if this is a normalization map, since if after I take a base change, I get something normal, it will actually map here. Okay, so if I prove that this map here is a normalization, I actually get a map to this guy, which is the quotient of a family of maximum variation by a finite group. Okay, I guess I could do it here. Okay, so how do I see this? So certainly this map is finite because this map is. And this one is normal, so really what I have to show is that this map is birational. And what I'm going to do is show that the general fibers are the same, and I have two families where the general fibers are the same, and they're over the same base. Okay. So how do I see that the general fibers are the same? So let me just write out what's going on. So there's sort of one thing in between here. Well, okay. So here we saw that the general fiber is just a pair of log general type. When I quotient by H, all I'm doing is doing a quotient on the base. So this is just identifying fibers that are the same. So the general fiber is not changing. And then I'm taking the quotient by the automorphism group. So the general fiber here is precisely just the pair of log general type quotient by the automorphism group, which is the same thing as a general fiber here, and thus the same thing as a general fiber here, because this is just a pullback. So I've shown that the general fibers are the same, and they're over the same base. So point. Right, so what this tells me is that, okay, I have xd over b. This maps into sigma. This maps into tau sigma delta d sigma. And I could take some base change here. Okay, so meant to take a base change. Okay. And now I could take this base change here. All right, so I'm going to define this b tilde by taking the fiber product here. Okay, so I have to draw a 3D diagram somehow. So the point is that after I take a base change, I get a map here. But since x tilde d tilde is normal, I actually get a map here. All right, so now what I do is I just take fibered powers. I get x tilde. Right, so I get a map to T. So now I have a map to a family which is a high fibered power of family of maximum variation by a finite group, and thus this is log general type by what I proved earlier. Right, so this proves theorem 1, the first theorem. So now all I have to show is that, like I said before, that the second theorem really follows as a consequence of the first. So this is for openly log canonical. And the idea is that this variety here of log general type really manifests a variety which is openly of log general type. I mean, essentially this one. The idea is that I have a birational map from here to here, and this one is big, and so by my definition of openly of log general type, so by definition of openly of log general type, since T tau sigma tilde n is of log general type, right? So then the map from tau sigma tilde to tau sigma shows that this one here is openly of log general type. Right, and so the point is that I don't actually need to take a birational modification to get a map to this one. So I get a map from xn dn. Right. Just by using the fact that B maps to the moduli space, and I take the universal family over that. That's what I wanted to talk about today. Thank you.